So organic formula, the first thing we usually get is empirical formula. Empirical formula. So empirical formula tells you the simplest ratio of each hydrocarbon. So it's usually CXHYOZ. Sometimes there might be nitrogen halogens, but the majority of the case it's just hydrocarbon with some oxygens. Yeah, so it gives you the simplest ratio of atom. Yeah, and then how do we get the simplest ratio of the atom? You usually do a combustion analysis. Yeah, so via combustion analysis. So via combustion analysis, it will tell you what's the mass of the original compound, and then how many carbon dioxide is formed, and then how many water is formed. Yeah, so from the mass of the carbon dioxide, you can work out the moles of carbon, and from the mass of hydrogen, you can work out the moles of hydrogen, and then from the mass of the compound. Yeah, because you know the total compound minus carbon minus hydrogen, the rest will just be all the mass, all the rest of the mass will just be oxygen, and then you can work out the moles of oxygen as well. Yeah, and then you just divide everything by the smallest number, you get the integer ratios, and then that's your empirical formula. Yeah, so you can get the empirical formula. And then from the empirical formula, if we know a little bit more information, we can get to molecular formula. So one empirical formula have infinitely many molecular formula. It will just be a multiple integer of C, X, H, Y, O, Z. Yeah, so the only way we go from empirical formula to molecular formula is via mass spectrometry. Yeah, so if you put your sample goes through a mass spectrometry, and then you can get the molar mass. Yeah, the highest peak on the mass spectrometry graph give you the molar mass. And then from the molar mass, and then we know the empirical formula, we can work out the molecular formula. Yeah. So once you get the molecular formula, molecular formula tells you exactly the number of atoms in the molecule. So you know how many hydrogen you have, how many carbon you have, and how many oxygen you have. Okay. And then from here, we can draw isomers. Yeah, so usually each molecular formula, again, you have infinite many. It's not infinite many, but you have like a lot of isomers. As n gets larger, the number of isomer gets larger as well. Yeah, and each isomer can be represented using 3 different notations. Yeah, so each isomer, you can use the structural formula to represent it. So for example, we have butane CH4, C4H10. Yeah, so that's one of the structural formula. And then we can also have the condensed formula. Yeah, So when you draw your condensed formula, you draw it based on each carbon. Okay, yeah. So this carbon, draw it in the first group, CH3, and then the next carbon, draw it in the next group, CH2, and then the next carbon, draw it in the next group, CH2. Yeah, and then the last carbon, draw it in the next group, CH3. Yeah, so all you do, you just ignore all the carbon-hydrogen bond. Okay, you ignore all the carbon-hydrogen and carbon-carbon bond. Yeah, and then the one we use the most, yeah, especially in spectroscopy, we usually just use Skeletal formula. That's ignore. So you ignore the carbon-carbon bond and then the carbon-hydrogen bond. Yeah, so skeletal formula is you ignore all the bond. Sorry, you don't ignore the bond, but you ignore all the hydrogens. Yeah, so it will just look like that. 1, 2, 3, 4. Yeah, so those three represent the same isomer. Okay. And then each line here represent a covalent bond. Yeah, carbon-carbon single covalent bond. Yeah. So let's just have a look at some examples. How can we go from structural formula to skeletal formula? Okay. So skeletal structure is used to show a simplified organic formula by removing all the hydrogens from the chains and then just leaving a carbon skeleton and associated functional groups. Yeah, so usually just 2 steps, and you just usually just remove the hydrogen, and then step 2 you just remove the carbon. Yeah, so this is one of the structural formula. Yeah, and then from this structural formula, we're trying to get the skeletal structure. So first of all, you remove all the hydrogen. So 1, 2, 3, 4, 5, 6. All this hydrogen get removed. So it just become carbon, carbon, carbon. And then just using a dot to represent the carbon, remove all the carbons. So represent every single carbon by a dot. And then this is your final skeletal structure. Yeah, and then just several mistakes. First of all, you can't draw it like this. Yeah, because triple bond is linear, you can't have this bond angle here. Okay, so this is wrong because triple bond has no bond angle. Yeah, the triple bond angle is 180 degrees, so you must draw it straight. You can't draw it like the single bond version. Okay. Yeah, so that's the first thing. Now let's draw the next one. Yeah, so you have a cyclohexane ring and with alcohol group. Yeah, again, the first thing is you just remove all the hydrogens. Yeah, so circle all the hydrogens and then remove all the hydrogens. Yeah. Yeah. However, this structure here is incorrect. Yeah, you can only remove all the hydrogens associated with carbon and the hydrogen associated with any other things. Oh, sorry, yeah, there should be another hydrogen here. Thank you. Yeah, you can only remove hydrogen associated with the carbon. Any hydrogen associated with any functional groups, okay, or any other atoms except carbon, you must keep it. Okay, you must keep it. Yeah, so the correct skeletal structure, and then we erase. So we can't ignore this hydrogen. You must add the hydrogen over there. Okay, and then you just erase the carbon. Yeah, so this is the correct final diagram. Yeah. Yeah. So just note. Yeah, you must keep all the hydrogen not attached to the carbon. Yeah, if the hydrogen not attached to the carbon, you must keep that. You can't get rid of them. Yeah, so I'll just quickly do several exercises and trying to draw the skeletal formula. Okay. Okay, so I just quickly draw the skeletal structure for those ones. First of all, you erase all the hydrogens. Yeah, because it's a skeletal structure. When you keep the carbon bond, yeah, you can't keep your carbon bond like that. Yeah. Like if you just draw the normal carbon like that, that's fine. But you can't have the skeletal structure look like that. Yeah. So if you draw a straight chain like that, and sometimes if you didn't draw it clearly, just draw a straight line, the number of carbon in the chain is not clear. Okay. So that's the first mistake. Never do that. Okay. Yeah. So if you just look at the structure here, I have no idea how many carbons there are. And then we talked about yesterday, the bond angle is 109.5 degrees. Yeah, so between each carbon and the other carbon, yeah, the bond angle here is 109.5 degrees. So you need to clearly show that bond angle there. So when you draw the correct structure, it should look like that. Yeah. So you can go up or down or go down and up. Those two are both fine, but you need to show the bond angles. Okay. Yeah, so you need to show the correct bond angles. Yeah. And then never indicate any hydrogen bond. Yeah. So for example, the second one. Yeah. So you understand the triple bond is a straight line. So you just go, okay. So that's a straight line. Triple bond. Okay. And then the first one has 3 hydrogens, and you just draw 3 bonds. It never ever indicates the hydrogen carbon bond. Okay, yeah, so never does that. Yeah. So the correct skeletal structure is the one without the carbon hydrogen bond. So it should look like this. Yeah, so this is a perfect skeletal structure for this formula. Yeah. And then the last one, you might say, oh, just get rid of all the hydrogens and then forgot about this nitrogen, and then just draw it too quickly, and then you get something like this. Yeah, so the mistake is with this nitrogen here. Yeah, because nitrogen is not a carbon, so you must make sure all the hydrogen attached to it is clearly drawn. Okay. Yeah, so there are 2 ways to draw it. You can just draw NH2, or you can indicate the bond. Okay. Yeah, so you can go like this. That's fine. Or if you're lazy, you can just draw here and then left with NH2. Yeah, so both of them is fine, but you must make sure the hydrogens are over there. Yeah, and another one is for aldehyde or acid. It's not really for acid, just only for aldehyde. Okay. So aldehyde, the hydrogen must be drawn. Okay. This is one of the exceptions. Yeah. So for example, you have propanol. Okay, you might think, okay, yeah, let's just draw this. One, two, three carbon and the oxygen. Okay, yeah. So if you follow all the previous rules, this is correct. There's nothing wrong with the previous rules. It's just for aldehyde, the hydrogen must be drawn. Okay, so this is incorrect. You must indicate the position of hydrogen. Okay, so it needs to look like this. Yeah, so this is the correct diagram for aldehyde. Yeah, and then the last one for benzene. Yeah, so for benzene, we know it looks like this. Yeah, so 6 carbons and 6 hydrogens are rounded. Yeah, so there are 2 ways to draw it. You can draw it like this, but it has a resonance structure goes in the other direction. Yeah, and both is fine. And then the equivalent diagram to represent both resonance structure, which is this one. Yeah. So you have a benzene ring here, and this cycle just represent those three double bond is not actually localized in the molecule. They are delocalized on top of this carbon ring. And so theoretically for benzene, you don't really have any carbon-carbon single bond or carbon-carbon double bond, just 1.5 bond throughout the structure. Okay. So if you do experiment, investigate those 6 bond in terms of bond strength, bond length, and bond energy, they're all identical. Okay, yeah, so the best way to draw the benzene ring is just using this structure here. Okay. And benzene ring, it has 3 symmetrical centers. Okay, so this is the first symmetrical line, and then this is the second symmetrical line, and then this is the third symmetrical line. Okay. So there are 3 symmetrical centers along this benzene ring. Yeah. And does anyone has any other questions about skeletal structures? Okay, and then the last one for skeletal structure is sometimes if you have optical isomers, and then the stereo center must be labeled properly in the skeletal structure. Yeah, so you need to explicitly label all the stereo carbons. Yeah. So all the stereo carbons must be labeled properly. Yeah. Not just the stereo carbon, any stereo atoms. Yeah, sometimes it may not be a carbon. You need to properly label it. Okay. So although we should erase all the hydrogens, however, you see here you have a stereo center, right? So this is a chiral carbon. This chiral carbon connect to 4 different groups: a methyl group, a hydrogen group, an amine group, and the acid group. So it connect to 4 different groups. So this is a chiral carbon. So you need to ignore these 4 hydrogens. Yeah, but you can't ignore those two hydrogen because they are connected to nitrogen, and you can't ignore this carbon. You can't ignore this hydrogen because we can't ignore this hydrogen either. Yeah, we can't ignore this hydrogen here because it indicates whether that's a R isomer or S isomer. Okay? So we must keep that hydrogen over there. Yeah, so just want to draw. First of all, you know the 3 hydrogens. Yeah, and then we just ignore all the carbons. Yeah, so this is the final skeletal structure. The final skeletal structure should look like this. So let's just quickly do 3 quick exercises. I will draw the 3 skeletal structures and try to turn them into structure formula. Okay. Yeah, everyone please give it a go. And then once you finish, type a 2 to the Skype chat. Yeah, so I didn't draw any of the hydrogens out. I just put the carbons. You can draw the hydrogens if you want. You literally just replace every single dot, right, every single dot by a carbon. Okay, and this here, just notice this is the ketone. Okay, this is not the aldehyde, because if it is aldehyde, you must draw it like that. So if you draw it like that, this would be aldehyde. And the structure formula should look like this. And then also, when you have a double bonded oxygen, double bonded oxygen is in a trigonal planar. So the geometry is called trigonal planar. Yeah, so when you draw the skeletal structures, it should be 120 degrees, 120 degrees, and 120 degrees. Yeah, so they should all be 120 degrees when you draw the carbonyl groups. Okay, so anything with a double bonded oxygen is called the carbonyl groups. Yes, that's just all the skeletal structures. Yeah, and then the last one, there's 3 carbon in a ring, so that's just cyclopropyl. And then for this benzene ring, yeah, usually for benzene ring you can just leave it as a benzene ring, but if you want to draw it out, just 6 carbons and then double, single, double, single, double, single. Yeah. So this is a conjugated double bond.